day, grade 10s. In this lesson, we will learn more about the information that the periodic table stores for us. We start with a study of the periodicity of halides. As we know, the group 7 elements fluorine, chlorine, bromine, and iodine are known as the halogens. The halogens react quite easily with other elements. When they react with a metal, they form an ionic salt. These metal salts are called halides. The most common halide is sodium chloride, known as table salt. The ratio of halide ions to metal ions depends on the valency of the metal ions. Valency is defined as a measure of an atom's ability to bond. We can use the periodic table to determine the valency of an element. We know that the group number of the periodic table tells us the number of valence electrons in an atom. For groups 1 through to 3, this is the same as the valency of the atom. In other words, how many bonds the atom can make. The halogens are in group 7. This means that they have 7 valence electrons. A halogen atom needs to accept 1 electron in order to fill the outer energy shell. Therefore, the valency of the halogens is -1. We can draw up a table to summarize this information. We know the valency of elements in groups 1, 2, and 3. We also know that the halogens are in group 7 and have a valency of -1. We can now use this table to write general formulae for the metal halides. If a metal from group 1 combines with the halogen, the ratio is 1 to 1, so the formula is Mx. If a metal from group 2 combines with the halogen, we need 2 halogen atoms for each metal atom, so the formula is Mx2. So, it makes sense that if a metal from group 3 combines with the halogen, the formula will be Mx3. Now let us use this to look at a few examples. Let us look at an example of what happens when lithium in group 1 combines with bromine, which is a halogen. We now know that when we combine a metal from group 1 and a halogen, the formula is Mx. Therefore, it is easy to see that the formula for lithium bromide is LiBr. Here is another example. Work out the formula for aluminium chloride. Since aluminium is in group 3, it has a valency of 3. When we combine an element from group 3 with the halogen, the formula is Mx3. Therefore, we write aluminium chloride as AlCl subscript 3. Now we will use the same technique to investigate the periodicity of oxides. Oxides are compounds formed when a metal bonds with oxygen. Oxygen is in group 6. Oxygen has 6 valence electrons and needs 2 electrons to fill its outer orbital. This means that oxygen has a valency of -2. Here is a similar table to the one we used before. This time we use oxygen and we work out the formulae of the metal oxides. When a metal in group 1 combines with oxygen, there is a ratio of 1 to 2. That means that 2 metal atoms combine with each oxygen atom and the formula is M subscript 2O. If a metal in group 2 combines with oxygen, their valencies are equal but opposite in sign. Therefore, there is a 1-to-1 ratio and the formula is just MO. It is slightly more complicated when a metal in group 3 joins with oxygen, but a simple diagram will help you understand it. A metal in group 3 has a valency of 3, therefore it can make 3 bonds. Oxygen has a valency of -2, so it can make 2 bonds. When a group 3 metal combines with oxygen as depicted here, you can see that the metal is left with a free bond. Another oxygen atom uses one of its bonds to join onto the metal, which now leaves the oxygen with a free bond. Now another metal atom uses one of its bonds to join onto this molecule, which leaves it in turn with 2 free bonds. These last 2 bonds are finally bonded with another oxygen atom, which results in a complete molecule with no free bonds. It takes 2 metal atoms and 3 oxygen atoms to form the metal oxide formula of M subscript 2 O subscript 3. Here is a tip for a shortcut. Just swap the valencies over. M has a valency of 3, so write the 3 as a subscript to the O. O has a valency of 2. Write this as a subscript to the M. Well, that's enough about valencies. Let's find out about another 3 properties: ionization energy, electron affinity, and electronegativity.
Chemists recognized that the way an atom holds onto its electrons could explain why some elements combine more easily to form compounds than others. They conducted a series of experiments to measure how well different elements hold onto their electrons. Electrons can be removed from an atom by applying electrical energy to a sample of the element. The amount of energy required for different elements can be measured and compared. When an electron is removed from an atom, the atom becomes positively charged and is called an ion. The energy required to remove one electron from an atom to form a positively charged ion is called the first ionization energy. First ionization energy values for different elements were tabulated using these experiments. A graph that compares first ionization energy and atomic number is most helpful. In this graph, our atomic number is the independent variable and so is placed on the horizontal axis. The first ionization energy is the dependent variable and so is placed on the vertical axis. Now, take a careful look at the line graph of this data. Do you notice any patterns in this graph? Take a closer look at the group 1 metals highlighted here. All these elements have low first ionization energies. This means that it does not take much energy to remove one electron from any of these atoms to form a positively charged ion. The data tells us that an atom of any of these metals does not hold onto its only valence electron tightly. It's not surprising then that the group 1 elements are extremely reactive and that they combine very easily with other elements to form compounds. We also notice that the first ionization energy decreases as we move down the group. We notice that as we move down the group, that the valence electrons are more loosely held and that the most reactive elements are at the bottom of the group. If you look at the energy level diagram for sodium, you will see that by removing one electron, we now have no electrons in the third energy level, but the second and first energy levels are filled. The sodium ion has 10 electrons in the same electron configuration as the noble gas neon. Talking about noble gases, have a look at where they are found on the first ionization energy graph. Hey, all of the noble gases have very high first ionization energies. This means that it is very hard to pull out a single electron from one of these atoms. The electrons are very tightly held. Can you see how this helps explain why these elements do not combine to form compounds? Notice that the first ionization energies decrease going down the group, just like the group 1 elements. So, the elements at the bottom of group 8 hold onto their valence electrons less tightly. Now that we have looked at a pattern of first ionization energies down 2 groups, let's see how the ionization energy changes as we move across the period. We'll start with period 2, starting at lithium, ending at neon. Do you notice that the ionization energy increases overall as we move across the period? Neon's first ionization energy is much higher than lithium's, but there are 2 interesting exceptions within this general trend. Boron, which is in group 3, has a lower ionization energy than beryllium, which is in group 2, and oxygen, which is in group 6, has a lower ionization energy than nitrogen, which is in group 5. We can explain these exceptions by looking at their energy level diagrams. The electron configuration for boron is 1s2, 2s2, 2p1. The electron configuration for beryllium is 1s2, 2s2. It is easier to remove one electron from the 2p orbital from boron than it is to remove an electron from the filled orbitals for beryllium, which is why boron has a lower first ionization energy than beryllium. For oxygen in group 6, the electron configuration is 1s2, 2s2, 2p4. For nitrogen in group 5, the electron configuration is 1s2, 2s2, 2p3. In the nitrogen energy level diagram, the p sublevel is half filled. For oxygen, we have one more electron in this sublevel. This means we have a single pair of electrons in a p orbital. Paired electrons repel each other because they are both negatively charged. In the case of a single pair, this makes it easier to remove the last electron from the atom. This explains why oxygen has a lower first ionization energy than nitrogen. Now that we have accurately described this unusual pattern, let's take a look at the first ionization energies in the next period. Look carefully and you will see that the pattern we found for period 2 is repeated for period 3. We start with a very low value for sodium in group 1. The value for group 2 is higher, but dips for group 3. The values for group 4 and 5 are much higher, but group 6 again lower. Once again, the highest value is for group 8. I think this shows definite evidence that there is a repeating pattern for first ionization energies. But there is one final idea we need to confirm using ionization energy data. So far, we have only been looking at first ionization energies. That is, the energy required to remove one electron from an atom. But it is possible to remove more than one electron from a single atom. Here is a table of the energies needed to remove a second, third, and fourth electron from the atom. These are called the second, third, and fourth ionization energies. The elements in this table are from the third period in the periodic table. Can you see that for all of these elements, the ionization energy increases from first to second to third and is highest for fourth? This tells us that it becomes more and more difficult to remove the next electron. As more and more electrons are being pulled away, the nucleus's pull on the remaining electrons becomes so much stronger. Now, there's an interesting pattern between ionization energies for different groups of elements. Here is a graph drawn from the table. This will help us see the pattern. Let's look at sodium first, the blue line. There's a huge jump between the first and second ionization energies. It takes 9 times more energy to remove the second electron from the sodium atom than the first. To explain this, we need to look at the energy level diagram for sodium. When we remove one electron from the sodium atom, we've taken away its valence electron. The sodium ion formed now has a stable electron configuration, just like the noble gas neon. When we try to remove the second electron, it requires so much more energy because we are trying to remove one of the core electrons. This large difference between first and second ionization energies is also true for other group 1 metals. This means that there's a clear difference in the way that core electrons and valence electrons are held for other group 1 metals too. Now let's look at magnesium from group 2, the red line. Here, the energy required to remove the second electron is not much more than the value of the first ionization energy, but the third ionization energy for magnesium is 5 times more than the second ionization energy. To explain this difference in ionization energies, let's look at the energy level diagram for magnesium. These 2 electrons in the 3s orbital are valence electrons. To remove them requires the first and second ionization energies. But if we wanted to remove one more electron, we'd require much more energy because it's one of the core electrons. That's why all group 2 elements will require high third ionization energies. Now look at the graph for aluminium in group 3, the green line. I'm sure you can see that the biggest difference is between the third and fourth ionization energies. Can you see a pattern emerging?
What we notice is there is a large amount of energy required when we try to remove an electron which is not a valence electron. In other words, since aluminium is in group 3, there is a big jump between the third ionization energy and the fourth. Now let us discuss electron affinity. Electron affinity is defined as the change in energy that takes place when a neutral atom in its gaseous state accepts an electron to become an anion. Electron affinity is energy that is released. The bigger the electron affinity of an element, the more likely it is that an atom will accept an electron in a chemical reaction. When we look at a graph of electron affinities, we can definitely see a trend. For the elements in period 2, from lithium to fluorine, the general pattern is an increase in electron affinity. The same trend can be seen as we move from sodium to chlorine across period 3. The non-metals have a higher electron affinity than the metals. But why is this? Do you remember that as we move across a period from left to right, the atom radius becomes smaller? At the same time, the number of protons in the nucleus increases as we move across the period. There is a stronger force of attraction between the nucleus of the atom and the electrons of the atom next to it. The non-metal atoms in groups 5, 6 and 7 need only a few electrons to fill their outer energy levels. This means that they are more likely to accept electrons. It therefore makes sense that the halogens have the highest electron affinity and the noble gases with their full outer shells have the lowest. This picture neatly summarizes the electron affinity trend across the period table. Note that the electron affinity increases as we go up a group. The final topic in this lesson is electronegativity. The electronegativity of an element indicates how strongly an atom in a compound attracts a shared electron pair. The Pauling scale is one measure of electronegativity. On this scale, fluorine, the most electronegative element, is assigned an electronegativity of 4. And francium, which is the least electronegative, has an electronegativity number of 0,7. Let us look at a graph of the electronegativity values across the periodic table and see if we can see a trend. Notice a clear increase in the electronegativity values from left to right across a period. The reason for this is that the electronegativity value is directly related to the electron configuration of an atom. Remember, when atoms bond, they get a fuller outer energy shell of electrons. Again, because the non-metals in groups 5 and 6 and 7 need only a few electrons to fill the outer orbital, they are more likely to accept electrons and exert a stronger force of attraction on a shared electron pair. The metals on the left are more likely to donate an electron in order to obtain a full outer energy shell. They therefore exert a weaker force of attraction on an electron pair and have a low electronegativity value. If we again look at this graph, we see that the electronegativity values within a group decrease as we move down. As we move down the group, the atoms get a new outer energy shell. The inner electrons shield more, so the nucleus has a weaker force of attraction on a shared electron pair. This diagram summarizes how the electronegativity values change across the periodic table. Grade 10s, we have covered a great deal of information in this lesson. If we know how the periodic table works, it is a very useful tool and provides us with lots of information. You'll find more information about the periodicity of the periodic table at www.mindset.co.za/learn. Remember to try some of the questions in the task video too. Goodbye.